Hello everyone. Today we're going to talk about practical cryptography. Specifically, we're going to talk about how digital signatures and encryption work in cryptography schemes. What's the actual mathematics behind it? What's the logic behind it? And for this example, we're going to be looking at specifically the RSA cryptography scheme, which is arguably the most popular cryptography algorithm in existence. So RSA is a type of asymmetric cryptography, and what I mean by that is it has a public key and it has a private key. So it consists of two different components, and the private key stays with the user and the public key is shared out to the rest of the world. We're going to be thinking in terms of numbers and math, and the rest I will explain at the closer to the end how it translates into real world use cases. But basically, there are a few different numbers and a few sort of mathematical theorems that come into play to make RSA work as it is. Specifically, we will be selecting values for a few different variables: p, q, n, e, d, and phi of n. How these values are calculated, what we mean by that, I will walk you through it. Oh, and there's also the variable k. So generally, this algorithm, what it works off of, RSA, is based off the idea that it is really hard to factor a number into its primes. So for example, if you have like a really large number, RSA typically works off really large numbers. So things like numbers which are like 2048 bits long, or numbers which are like 4096 bits long. And these numbers are absolutely massive, right? If you have the largest number you can represent goes up exponentially the more bits you have. For example, if you only have 1 bit, then you can only represent two numbers, 0 or 1. But if you have 2 bits, you can now represent 4 numbers, right? You can represent 0, 0, 0, 1, 1, 0, and 1, 1, which is 0, 1, 2, and 3. So the more bits you add, the faster it grows and the more numbers you can start to represent. Specifically, you can represent 2 to the power the number of bits. So when we talk about 2048 bits, the largest number that is possible there is 2 to the power 2048 and 2 to the power 4096 over here, which are really, really, really large numbers. Okay? So typically RSA works off of really big numbers, and it goes off the idea that if you have a really large number that is a multiple of two prime numbers, right? So if you have, for example, just as an example, if we take the number 15, and this is a multiple of two prime numbers, 3 and 5, we can kind of figure out what this is coming from. However, the more you grow, the bigger and bigger sort of numbers you go towards. For example, if we do 17 into 19, which is equal to 323, it is easy to do multiplication, but prime factoring a number isn't so easy. So now you have to try a variety of different prime numbers that are smaller than this to try to figure out what the prime factor multiples of this number is. And now when we're talking about numbers that could be as large as these, prime factorization becomes a really, really hard problem that computers don't have a good way to solve for. And this is what secures the entire mathematics behind RSA. How it does that, let's take a look at it. So first of all, we need to choose two prime numbers, p and q. These will go into the multiplication. Typically, again, these are really large numbers, but for the sake of mathematics, so we can like show examples to you on this whiteboard, I'll pick somewhat relatively smaller numbers. So let's go p is equal to 53 and q is equal to 59. Okay, and then we calculate their product. This is called n, and n is a multiplication of p and q, and in this case it equals 3127. Okay, how we use these numbers, we're going to get into that. So all this time when we talk about the public key and the private key, and I said we're going to just think of them in terms of numbers, they actually consist of two numbers each. So the public key consists of two numbers n and e, and the private key consists of two numbers n and d. We haven't gotten into what d and e are right now, but we've calculated n, and this is how you calculate n. N is the multiplication of two prime numbers, which in reality are very, very large numbers. For e, we want to have typically a small number. I mean, I say small relative to 2 to the power 2048. In our example, we'll use the number 3, but typically the value you use for this in reality is 65537, which is equal to 2 to the power 8 plus 1. So we have chosen e, and this actually completes our public key. So we have both n and e now, and we have the components required to make the public key. So e is public, e is a small number, it is publicly known. Now for the private key, we need to calculate phi of n first, and I'll get into why we do this and what's the significance of this number. But phi of n, it's a value that is calculated using p minus 1 multiplied by q minus 1, and in our case it would be 52 times 58, which comes out to 3016. 6. So once we have phi of n, we pick a small number k, and k can be any integer. Typically it's a small integer. In our case we'll go with k equals 2, and finally we can now calculate d, which is the other part of our private key over here. D is calculated as k times phi of n and plus 1 whole divided by e. Alright, get into where this equation comes from. If we do the mathematics, if we do the calculations based on the numbers we have chosen, this will come out to 2011. Now let's talk about where this is coming from and basically what is going on over here. So where this is coming from, we'll take a slight detour, is there's this theorem called Eulers Theorem, and Eulers Theorem basically states that as you exponentiate a number x, which is to the modulus of n to the ith power, as I keeps increasing, as you keep increasing the number I, like 1, 2, 3, 4, 5, eventually you will come back to x, right? This whole equation, as I keeps increasing, eventually you will come back to x. And as you keep increasing I, eventually you get to congruency where x to the power I mod n is the same thing as x. And this fact is used within RSA to do encryption as well as digital signatures. So specifically, let's take a look at how the encrypted message looks, and then this chosen value of d will make a lot more sense. So if we do encryption, let's say we want to encrypt the letters hi, like the word hi, right? You have to choose a way of representing this in numbers. Let's just go with a simple way where we give them the numbers according to their position in the alphabet. So it will be 8 and 9. And let's call this 89, right? How you choose to convert letters into numbers depends on, like, you know, there are popular schemes like ASCII codes or like Unicode and things like that today. We'll just go with 8 and 9 based on their position in the alphabet. So let's say we want to encrypt the message 89. What we do is we calculate the encrypted data, let's call it C for Cipher. We calculate the cipher using the formula 89 to the power of E mod n, right? And what this gets us in our case is 89 cubed mod n. and n is 3127, right? And 89 mod cubed comes out to 89 mod cubed. This is 704969. So 704969 mod 3127. Let's go to Wolfram Alpha. 704969 mod 3127. And this comes out to 1394. Right? So 704969 mod n equals 1394. Okay, so the person who wanted to send a message to the owner of the private key, right? Let's say I'm the owner of the private key and you want to send me the message hi. You take my public key, this E and N are both parts of my public key. You take these two values and you calculate the ciphertext for me. So you take your message 89, you do to the power E mod n, they're both parts of my public key, and you now have the ciphertext 1394. You send this back to me, and on my end, what I can do is I can decrypt this data. We'll call this O for original message. We'll decrypt this data. What we'll do is we take the ciphertext, raise it to the power D, and do modulus n. Right, so D is the private key that only I have. So this becomes 1394 to the power, the value of D was 2011, so 2011 mod 3127. All right, this looks weird. You might not understand what's happening here. I'll explain this in just a second, but let's see if this comes out to what we expect it to be. So we do 1394 to the power 2011 mod 3127. And Wolfram Alpha tells us the result is 89, which was the original message you wanted to send to me. How does this work? What just happened over here? So, in the RSA algorithm, in the RSA keeper algorithm, the numbers are chosen in a way where, if you look at it, they follow this general property where for some value n and m to the power e to the power d, this is congruent to m to the power d to the power e just by basic exponential mathematics. And these two values, when done mod n, when done with modulus exponentiation, if we do mod n and mod n, this is actually congruent to m mod n directly. And since n is a really large number, because n is the multiple of p and q, which are both really large numbers, it's just congruent to m itself, as m needs to be less than n. So how does this property actually happen is because, again, I was talking about Eulers Theorem. So I said that x to the power I mod n will eventually be equal to x as I keeps increasing, right? So what we're saying over here is m to the power of dE mod n will eventually be equal to m itself. And it all is in the magic of the product of E and D. And this is where we go back to how we calculated D. So we picked E to be a small number, in our case 3. Realistically, it's something like 2 to the power 8 plus 1. And then we calculated D using this formula. We calculated D using k into phi n plus 1 over E. If you move the math around a little bit over here, we'll see that the multiplication of D and E equals k times phi of n plus 1, right? And this is actually Eulers' theorem, where Eulers' theorem states that the magic exponent, when we have this thing, in our case, this value is reached, the Eulers' theorem is reached when I grows to k times phi n plus 1. So for some value x to the power I mod n, this will be equal to x itself when I is equal to a times phi n plus 1. And we have phi n, we have 1, and we have the k. Going back, this also explains sort of why we chose k the way we did. Actually, the reason to choose k like 2, k being the value of 2, was to make the whole value of d an integer. Because if we just do phi n plus 1 over e, which is equal to 3016 plus 13017 divided by 3, you'll see it is 1005 point something something, right? It's not a whole number, so we multiply it by k to make it a whole number, in our case 2011, by multiplying phi n by 2. So k is any number that makes this a whole number, and once we have that as the whole number, we use it again in the for calculate dE, and according to Eulers theorem, this comes out and makes the equation true that m when raised to the power dE mod n was congruent to m again. So it just gives back m. And that's how we decided how to choose k and how to choose d, depending on the values of n, i.e. depending on the value of p and q. The value of k chosen is different, and it's kept private by the owner of the private key. So this is technically kind of something you hold along with the private key. And this is how encryption and decryption work in RSA. So just for a quick recap, the public key consists of two values n and d. The private key consists of two values n and d. N is the product of two prime numbers, p and q, which are very large numbers. E is chosen as an integer that is not a factor of n, so e must not be dividing n. In our case, 3 works for us. So we take the number 3 as e, and then we calculate d using this formula, k phi n plus 1 divided by e. And phi n is this calculation, p minus 1, q minus 1. So with these values in place, we come up with this interesting sort of mathematical principle applying Eulers theorem, that if we do a message to the power e mod n, and then we take that value and we further raise it to the power d, so c to the power d mod n, we get back the same original message that we ciphered in to calculate c. All right. Take your time to wrap your head around this. It's really just an application of modulus exponentiation and Euler's theorem, and it can be a little tricky to understand, but now you might be able to see what the bottleneck over here is. The bottleneck over here is that n and e are part of the public key. So n and e are known to the public. So the only thing keeping you safe is the value of d. If somebody knows the value of d, they can decrypt any message anybody is sending you. So it is important. That p and q must be chosen to be very large and secure numbers. If the values of p and q were not prime numbers, and if they were just like any random numbers, it makes it significantly easier to find factors for n, right? Because n, the larger the number is, the more easier it is to find factors for it. And if you remove the restriction that the factors both must be prime, it becomes really easy to find different factors for it. And if p and q itself aren't prime, then that means they must have their own prime factors, which means n will have more than 2 prime factors. So if the adversary can somehow compute p and q by deriving it from n, then they have everything they need to calculate the value of d, because then they can calculate phi of n, p minus 1, q minus 1, and calculate the value of d. So the only thing keeping you safe is how n is calculated, i.e. what are the prime numbers that went into creating the value of n, And as long as these two numbers are kept safe, D is safe, right? And this is why we must use the really, really large prime numbers to produce an even larger number, such that prime factorization on it is very hard to do. So as long as D is safe, you're safe. Otherwise, if somebody has D, they can decrypt all your messages. So this is how encryption and decryption works. Let's talk about signatures. How do digital signatures work in this world? So with encryption and decryption, the idea is somebody wants to send me an encrypted message. They take my public key, calculate a ciphertext with it, send me the ciphertext, and I can decode it back into the original message using my private key. Now, signatures solve a different problem. Signatures solve the problem of, if I want to send somebody a message, they should know that it is coming from me. And secondly, they should know that the message hasn't been altered in transit over the network, right? No malicious activity, like the message wasn't changed. What I sent you is what I actually sent you. The thing with encryption is you have to know your recipient beforehand, right? You need to know the public key of your recipient beforehand. So if you want to send me an encrypted message, you must know my public key before you actually send me the message. With signatures, however, we're solving a different problem. We're sending out a message to anybody in the whole world who wants to see it. We can send it to anyone, and they can know it's coming from me, even though I didn't have to do anything specific for them, right? So with signatures, we use the same Eulers theorem kind of helps us. So we have some message M, and we use the property that M to the power E to the power D mod N is congruent to M mod N for the values of E and D. So, and let's assume M is the message, right? M is the message hi again. So M equals hi, which equals 89, right? And how we do a signature, first of all, is we first calculate a hash of M, because the messages can be arbitrarily long and we'd prefer to do it over a hash. So we calculate H equals hash of M using any hashing algorithm, like SHA-256 or whatever. And then we can calculate the signature S using H power D mod N. All right, so the signing part is done using the private key. So if I need to send a signed message out to the rest of the world, I need to use my private key, and I'll raise the hashed message to the power of D mod N, and I'll send this out to the rest of the world. So to the rest of the world, what I actually give is I give them two values. I give them the original message, and I give them the signature over it, right? So I make this public, because I'm sending this out to everybody. I make my original message as well as my signature over it public. And anybody else, what they can do to verify it is they can take this original message and recalculate the hash for it. So they can recalculate the hash of M, and then they can decrypt the signature. They can decrypt the signature, let's call it H dash. They can decrypt the signature using S to the power E mod N. And again, think about what just happened here. So this is basically H to the power D to the power E mod N. And because of our choice of E and D and Eulers theorem again, we basically end up at H again. So if we can use the person's public key over their signature to get back to the hash of M, and H dash is equal to H, this means that M is the original message, right? Because if I was sending you some message and I signed over it, but then while it was being sent to you, somebody changed M. Somebody I don't know, I was sending you a nuclear launch code and somebody stole it and they changed the code with something else. When you go to verify the message, when you calculate the hash of the message you end up receiving, which is not the original message, it will be different from the h dash you calculate from my public key. And in that case, you can be assured that what you got isn't the message that I sent you, right? And this is how signatures work with RSA. All of this comes down to Eulers Theorem and the properties of modulus exponentiation. So originally, the values we were choosing for these numbers looked quite vague and looked quite weird. Why are we doing this? But as you see the application, you realize that the numbers that we chose actually have pretty significant meaning. It is important for these two numbers to be really large primes to make an even larger resulting number n. E is typically a small integer that's not a factor of n, and we calculate d such that we can apply Euler's theorem on it such that it's phi n plus 1, so that we can hold this x to the power I mod n is congruent to x for a certain value of I, where the multiplication of d and e is the value of I that we use. All right, take some time to wrap this in. Thank you so much for watching. This has been Practical Cryptography, RSA, Digital Signatures and Encryption. Check out LearnWeb3 if you want to learn more, and I'll see you in the next one.